A corona is an aura of plasma that surrounds the Sun and other celestial bodies. The Sun's corona extends millions of kilometers into space and is most easily seen during a total solar eclipse. But it is also observable with a coronagraph. The word corona is a Latin word meaning crown, from the ancient Greek kappa omicron rho omega nu eta. The high temperature of the Sun's corona gives it unusual spectral features, which led some in the 19th century to suggest that it contained a previously unknown element, coronium. Instead, these spectral features have since been explained by highly ionized iron. Bengt Q10, following the work of Grotrian, first identified the coronal lines in 1940 as transitions from low-lying metastable levels of the ground configuration of highly ionized metals. These high stages of ionization indicate a plasma temperature in excess of 1 million Kelvin, much hotter than the surface of the Sun. Light from the corona comes from three primary sources, which are called by different names although all of them share the same volume of space. The K-corona is created by sunlight scattering off free electrons. Doppler broadening of the reflected photospheric absorption lines completely obscures them, giving the spectral appearance of a continuum with no absorption lines. The F-corona is created by sunlight bouncing off dust particles, and is observable because its light contains the Fraunhofer absorption lines that are seen in raw sunlight. The F-corona extends to very high elongation angles from the Sun, where it is called the zodiacal light. The E-corona is due to spectral emission lines produced by ions that are present in the coronal plasma. It may be observed in broad or forbidden or hot spectral emission lines and is the main source of information about the corona's composition. Physical features. The Sun's corona is much hotter than the visible surface of the Sun. The photosphere's average temperature is 5,800 Kelvin compared to the corona's 1 to 3 million Kelvin. The corona is 10⁻12 times as dense as the photosphere, and so produces about 1/1,000,000th as much visible light. The corona is separated from the photosphere by the relatively shallow chromosphere. The exact mechanism by which the corona is heated is still the subject of some debate, but likely possibilities include induction by the Sun's magnetic field and MHD waves from below. The outer edges of the Sun's corona are constantly being transported away due to open magnetic flux generating the solar wind. The corona is not always evenly distributed across the surface of the Sun. During periods of quiet, the corona is more or less confined to the equatorial regions, with coronal holes covering the polar regions. However, during the Sun's active periods, the corona is evenly distributed over the equatorial and polar regions, though it is most prominent in areas with sunspot activity. The solar cycle spans approximately 11 years, from solar minimum to the following minimum. Since the solar magnetic field is continually wound up, sunspot activity will be more pronounced at solar maximum where the magnetic field is more twisted. Associated with sunspots are coronal loops of magnetic flux, upwelling from the solar interior. The magnetic flux pushes the hotter photosphere aside, exposing the cooler plasma below, thus creating the dark spots. Since the corona has been photographed at high resolution in the X-rays by the satellite Skylab in 1973, and then later by Yoko and the other following space instruments, it has been seen that the structure of the corona is quite varied and complex. Different zones have been immediately classified on the coronal disk. The astronomers usually distinguish several regions, as described below. Active regions are ensembles of loop structures connecting points of opposite magnetic polarity in the photosphere, the so-called coronal loops. They generally distribute in two zones of activity, which are parallel to the solar equator. The average temperature is between 2 and 4 million Kelvin, while the density goes from 109 to 1010 particle per cc. Active regions involve all the phenomena directly linked to the magnetic field, which occur at different heights on the Sun's surface. Sunspots and faculae, happening in the photosphere, spicules, H-alpha filaments and plages in the chromosphere, prominences in the chromosphere and transition region, and flares and coronal mass ejections happening in the corona and chromosphere. But if flares are very violent, can perturb also the photosphere and generate a Morton wave, as described by Ukeda. On the contrary, quiescent prominences are large, cool dense structures which are observed as dark, snake-like, H-alpha ribbons on the solar disk. Their temperature is about 5000–8000 K, and so they are usually considered as chromospheric features. In 2013, images from the high-resolution coronal imager revealed never-before-seen magnetic braids of plasma within the outer layers of these active regions. Coronal loops are the basic structures of the magnetic solar corona. These loops are the closed magnetic flux cousins of the open magnetic flux that can be found in coronal hole regions and the solar wind. Loops of magnetic flux well up from the solar body and fill with hot solar plasma. Due to the heightened magnetic activity in these coronal loop regions, coronal loops can often be the precursor to solar flares and coronal mass ejections. Solar plasma feeding these structures is heated from under 6000 K to well over 1 × 106 K from the photosphere, through the transition region, and into the corona. Often, the solar plasma will fill these loops from one foot point and drain from the other. When the plasma goes upward from the foot points towards the loop top, as it always occurs during the initial phase of a compact flare, it is defined as chromospheric evaporation. When the plasma rapidly cools falling down towards the photosphere, we have the chromospheric condensation. There may also be symmetric flow from both loop foot points, causing a build-up of mass in the loop structure. The plasma may cool rapidly in this region, creating dark filaments in the solar disk or prominences off the limb. Coronal loops may have lifetimes in the order of seconds, minutes, hours or days. Usually coronal loops lasting for long periods of time are known as steady-state or quiescent coronal loops, where there is a balance in loop energy sources and sinks. Coronal loops have become very important when trying to understand the current coronal heating problem. Coronal loops are highly radiating sources of plasma and therefore easy to observe by instruments such as TRACE. They are highly observable. Laboratories to study phenomena such as solar oscillations, wave activity and nanoflares. However, it remains difficult to find a solution to the coronal heating problem as these structures are being observed remotely, where many ambiguities are present. In situ measurements are required before a definitive answer can be arrived at, but due to the high plasma temperatures in the corona, in situ measurements are impossible. The next mission of the NASA Solar Probe Plus will approach the Sun very closely, allowing more direct observations. Large-scale structures are very long arcs which can cover over a quarter of the solar disk but contain plasma less dense than in the coronal loops of the active regions. They were first detected in the June 8, 1968 flare observation during a rocket flight. The large-scale structure of the corona changes over the 11-year solar cycle and becomes particularly simple during the minimum period, when the magnetic field of the Sun is almost similar to a dipolar configuration. Interconnections of active regions. The interconnections of active regions are arcs connecting zones of opposite magnetic field, in different active regions. Significant variations of these structures are often seen after a flare. Some other features of this kind are helmet streamers, large cap-like coronal structures with long pointed peaks that usually overlay sunspots and active regions. Coronal streamers are considered as sources of the slow solar wind. Filament cavities. Filament cavities are zones which look dark in the X-rays and are above the regions where H-alpha filaments are observed in the chromosphere. They were first observed in the two 1970 rocket flights, which also detected coronal holes. Filament cavities are cooler clouds of gases suspended above the Sun's surface by magnetic forces. The regions of intense magnetic field look dark in the images because they are empty of hot plasma. In fact, the sum of the magnetic pressure and plasma pressure must be constant everywhere on the heliosphere in order to have an equilibrium configuration. Where the magnetic field is higher, the plasma must be cooler or less dense. The plasma pressure can be calculated by the state equation of a perfect gas, where is the particle number density, the Boltzmann constant and the plasma temperature. It is evident from the equation that the plasma pressure lowers when the plasma temperature decreases respect to the surrounding regions or when the zone of intense magnetic field empties. The same physical effect makes sunspots dark in the photosphere. Bright points are small active regions spread over the whole solar disk. X-ray bright points were first detected in April 8, 1969 during a rocket flight. The fraction of the solar surface covered by bright points varies with the solar cycle. They are associated with small bipolar regions of the magnetic field. Their average temperature ranges from 1.1 mK to 3.4 mK. The variations in temperature are often correlated with changes in the X-ray emission. Coronal holes. Coronal holes are the polar regions which look dark in the X-rays since they do not emit much radiation. These are wide zones of the Sun where the magnetic field is unipolar and opens towards the interplanetary space. The high-speed solar wind arises mainly from these regions. In the UV images of the coronal holes, some small structures, similar to elongated bubbles, are often seen as they were suspended in the solar wind. These are the coronal plumes. More exactly, they are long thin streamers that project outward from the Sun's north and south poles. The quiet Sun, the solar regions which are not part of active regions, and coronal holes are commonly identified as the quiet Sun. The equatorial region has a faster velocity rotation than the polar zones. The result of the Sun's differential rotation is that the active regions always arise in two bands parallel to the equator, and their extension increases during the periods of maximum of the solar cycle, while they almost disappear during each minimum. Therefore, the quiet Sun always coincides with the equatorial zone and its surface is lower during the maximum of the solar cycle. Approaching the minimum of the solar cycle, the extension of the quiet Sun increases until it covers the whole disk surface, excluding some bright points on the hemisphere and the poles, where there are the coronal holes. Variability of the corona. A portrait as diversified as the one already pointed out for the coronal features is emphasized by the analysis of the dynamics of the main structures of the corona, which evolve in times very different among them. Studying the coronal variability and its complexity is not easy because the times of evolution of the different structures can vary considerably, from seconds to several months. The typical sizes of the regions where coronal events take place vary in the same way, as it is shown in the following table. Flares take place in active regions and provoke a sudden increase of the radiative flux emitted from small regions of the corona. They are very complex phenomena, visible at different wavelengths. They interest several zones of the solar atmosphere and involve many physical effects, thermal and not thermal, and sometimes wide reconnections of the magnetic field lines with material expulsion. Flares are impulsive phenomena, of average duration of 15 minutes, even if the most energetic events can last several hours. Flares involve a high and rapid increase of the density and temperature. An emission in white light is only seldom observed. Usually, flares are only seen at EUV wavelengths and in the X-rays, typical of the chromospheric and coronal emission. In the corona, the morphology of flares, which can be grasped from the observations in the soft and hard X-rays, at the UV wavelengths and in H-alpha, is very complex. However, two kinds of basic structures can be distinguished. Compact flares, when each of the two arches where the event is happening maintains its morphology. Only an increase of the emission is observed without significant structural variations. The emitted energy is of the order of 1022 to 1023 J. Flares of long duration, associated to eruptions of prominences, transients in white light, and two-ribbon flares. In this case, the magnetic loops change their configuration during the event. The energies emitted during these flares of such large proportions can reach 1025 J. As for temporal dynamics, three different phases are generally distinguished, whose duration are not comparable. These times, moreover, can depend on the range of wavelengths used to observe the event even considerably. An initial impulsive phase, whose duration is of the order of minutes. Strong emissions of energy are often observed even in the microwaves, at EUV wavelengths and in the hard X-rays. A maximum phase, a decay phase, which can last several hours. Sometimes also a phase preceding the flare can be observed, usually called as pre-flare phase. Transients accompanying solar flares or large solar prominences, coronal transients, are sometimes released. These are enormous loops of coronal material traveling outward from the Sun at over 1,000,000 kilometers per hour, containing roughly 10 times the energy of the solar flare or prominence that accompanies them. Some larger ejections can propel hundreds of millions of tons of material into space at roughly 1.5 million kilometers an hour. A solar storm. These movies have been taken by the satellite SOHO during 2 weeks in October and November 2003. The images have been taken at the same time by the different instruments on board SOHO. The MDI, producing magnetograms, the Extreme Ultraviolet Imaging Telescope, which photographs the corona in the ultraviolets, and the Large Angle and Spectrometric Coronagraph. The first video at the top on the left shows the magnetograms as they vary in time. At the top on the right, the photosphere can be seen in white light as taken by the MDI. Furthermore, the EIT filmed the event in its 4 filters, which are sensitive to different wavelengths, selecting plasma at different temperatures. The images in orange refers to chromospheric plasma, while that one in green to the corona. In the last movie at the center, the Sun's images taken in the ultraviolet filter by the EIT have been combined with those taken by the coronagraph, LASCO blue and white in this movie. All the instruments registered the storm, which is considered as one of the largest solar activity events observed by SOHO and maybe since the advent of space-based solar observations. The storm involved all the plasma of the solar atmosphere from the chromosphere to the corona, as can be seen from the movies, which are ordered from left to right, from top to bottom, in the outward direction of the increasing temperature on the Sun. Photosphere, chromosphere, transition region, low corona and extended corona. The corona is visible to the SOHO, LASCO coronagraph instruments, which block the bright disk of the Sun, so the significantly fainter corona can be seen. In this movie, the inner coronagraph is combined with the outer coronagraph. As the movie plays, we can observe a number of features of the active Sun. Long streamers radiate outward from the Sun and wave gently due to their interaction with the solar wind. The bright white regions are visible due to their high density of free electrons, which scatter the light from the photosphere towards the observer. Protons and other ionized atoms are there as well, but are not as visible since they do not interact with photons as strongly as electrons. Coronal mass ejections are occasionally observed launching from the Sun. Some of these launch particle events can saturate the cameras with snow-like artifacts. Also visible in the coronagraphs are stars and planets. Stars are seen to drift slowly to the right, carried by the relative motion of the Sun and the Earth. The planet Mercury is visible as the bright point moving left of the Sun. The horizontal extension in the image is called blooming and is due to charge leakage during readout of saturated pixels in the camera CCD imager. Stellar coronae. Coronal stars are ubiquitous among the stars in the cool half of the Hertzsprung-Russell diagram. These coronae can be detected using X-ray telescopes. Some stellar coronae, particularly in young stars, are much more luminous than the Sun's. For example, FK Coma Berenices is the prototype for the FK Com class of variable star. These are giants of spectral types G and K with an unusually rapid rotation and signs of extreme activity. Their X-ray coronae are among the most luminous and the hottest known, with dominant temperatures up to 40 Mk. The astronomical observations planned with the Einstein Observatory by Giuseppe Varna and his group showed that F, G, K and M stars have chromospheres and often coronae much like our Sun. The OB stars, which do not have surface convection zones, have a strong X-ray emission. However, these stars do not have coronas, but the outer stellar envelopes emit this radiation during shocks due to thermal instabilities in rapidly moving gas blobs. Also, A stars do not have convection zones, but they do not emit at the UV and X-ray wavelengths. Thus they appear to have neither chromospheres nor coronae.